All right. So, looks like I need to update the date because Wednesday is the 1st, right? 1st. All right, so your 3 reservoirs assignment is due 2 days from today. And we've just finished that binder check. We're going to continue working the example problem that was in that recorded lecture for Friday, simply because in the recording it didn't go all the way through calculating the pressure at the junction. So it had finalized calculating the flow rates and it had converged on F values, but we need to just do the practice of calculating the pressure at the junction one more time. So I hope everybody watched that video for Friday's class. And today what we'll do is speak a little bit about local losses, which comes from section 4 of chapter 8 in the book. And then if we've got some additional time, we're going to get some additional practice trying to enhance our accuracy on the Moody diagram. Some people do pretty good on the Moody diagram. Other people are using, I think, maybe thick markers or crooked rulers and end up with F values that are a little bit out of range. So we'll get some extra practice on that. Any announcement questions before we move on? Okay, so let's go back then just to this example where we had left it off in the recorded video was, just to set the stage. Here we've got the 3 reservoirs. Our initial guess was 111 feet, which we did the flow balance and found that that was too high. So then lowering it to 109 feet made things a little bit different because one of these pipes that had previously been an outflow became an inflow. So this junction DA, if D has 111 feet of head, the water is going to flow from D towards A. But now if we had to lower our guess, which was the conclusion we came to at the end of iteration 1, so we say 109 feet is the amount of head at D. Now that changes the flow from D to A to the other way around. So I guess I could emphasize that by showing you now the flow goes this way if it is 109 feet. So just to point out that most of these formulas stayed the same except that when I'm calculating the out minus the in, I have to make note that AD was an outflow in the first iteration, but in the second iteration it's flowing into the junction. Therefore the label changed accordingly and this calculation. So then at 109 feet, the guess was too low, so we overshot, need to raise it. So I did goal seek to find convergence. Now I've got no difference between the outflow and the inflow, but I wasn't satisfied. I still went for an iteration 4 because this F value changed a little bit more than I was comfortable with. The F value for these pipes has more or less converged, but the F value for pipe AD hasn't converged very tightly, and it's mainly because it's a low flow rate pipe. There's not much flow going through it. So I went all out and did a 4th iteration. Of course, the flow rate is more or less the same. I did the what if analysis and goal seek and had it converge another time, but at least now my F values have more or less converged. If you see 0.027, 0.027, so we're all good. Now, part 2 of this example, which we didn't get to in the recorded video on Friday's class, was, so then what does that mean is the pressure at the junction? If we know the junction's elevation is 85 feet, and we've now calculated how much head is at that junction, then how much pressure is at the junction? And so it starts off with us putting in the known elevation of the junction. Oops, that's the head. So I need to have just a reference up here to the head that was calculated at D. Type in the elevation of that junction, 85 feet. Now velocity head, the reason why I calculate 3 different velocity heads is I've got 3 different, 2 diameter pipes, but there's a different velocity going through DC. So I'm going to average the velocity head in each of the pipes because the junction is where the 3 pipes come together. So the question is, even though velocity head is relatively minor, if I'm going to include it in the calculations, I might as well have it be a blended velocity head for the 3 pipes that are feeding junction D. Okay, so the velocity head in AD is, velocity head is V squared divided by 2G. So the velocity in pipe AD is this squared divided by 2G, 2 times 32.2, since we're working in traditional units. So it says 0. That's because there's a really low velocity. If I have it show more units, there is some number there, but there's just not very much energy in that pipe. Velocity head in pipe D, BD, so velocity squared divided by 2G. And then the velocity head in the other pipe, I guess I could just drag that formula down, and it's going to look at the velocity in the correct place, velocity DC. Okay, so then the average velocity head between the 3 pipes, and so now I'm going to subtract out the velocity head at junction D from the head along with the elevation, and then multiply it by the unit weight of the fluid to find the pressure at D. So using this formula. So the pressure at D is the overall head. I guess I ought to put the parentheses to start because I'm going to multiply it by unit weight at the end. It's the head minus the elevation minus the average velocity head, and then multiplied by the unit weight of water, 62.4. Okay, so we've got the pressure head in terms of pounds per square foot, and then to find pounds per square inch, we divide by 144. All right, so 10.3 PSI should be what we get as the pressure there at D, junction D. Now you've got in the homework that's due on Wednesday 2 problems where you use this Darcy-Weisbach method, and then the third problem where you're creating an example of your own using the Hazen-Williams. So are there any general concept questions that you'd like to ask before we move on from the 3 reservoirs?
For problem 2 in the homework, we're given the height of the junction.
Okay.
That would mean that if we work all the equation out, the error column there should turn to 0 by what's given, correct?
This error, so you're saying you're given the Z?
Yeah, that's essentially what we found using this method in problem 1. So if we're given that,
remember
we're given
that
the Z, we're not given
the head.
Okay,
Yeah,
that makes sense.
Okay, yeah, you're given the physical elevation so you can calculate the pressure,
Perfect.
but that's not the same as the
Right.
the head. Okay. Other questions? Yeah.
The F value being not identical, is there a percentage basis that's used, or just a rounded for so many digits?
Good question. Let's just see what is the percentage difference, because that looks pretty different, but on a percentage basis, I think it may be relatively small. So let's just explore that, because that's an important question. So the difference divided by the new one times 100. So that's only a 1% change between the two, 1.02%. It's good enough. Yeah.
Do we use like a 1%?
Yeah, use a 1% as a convergence criteria. Now, the truth is that for a pipe that has so little flow going through it, even like 2 or 3% would still give us an acceptable estimate of what's the pressure and what are the flow rates. So 1% is definitely good enough when you've got a flow rate this low. Now, if there's a pipe that has a high flow rate through it, like this pipe DC, it's got a lot of flow through it, so it's more important for that one to be accurate, but it was more accurate to begin with anyway. So it kind of goes hand in hand. The pipes that have more flow going through them will converge more quickly and more accurately than these low flow pipes. And you'll see the same thing when we do a method called the Hardy-Cross method I think maybe later this week on Friday we'll do the Hardy-Cross method doing spreadsheets, and we'll have lots of pipes. We won't just have 3, but we'll have entire pipe networks. And the tricky ones, the ones that are hardest to converge, is the one that has very little flow going through it, because we'll apply some correction, and whatever correction we apply is pretty large compared to the low flow. So that's maybe a little more inside baseball than you need right now. But as far as your question, like how do you know when to quit with the convergence, 1% is a good rule of thumb. And if it's like 1.5% and you don't feel like doing another iteration, I'll probably understand.
I didn't know, and I didn't change the answer.
Okay, yeah. If you did an iteration 5, you'd still get the same heads, you'd still get the same pressure. Good question. Are there any others? All right. So let's talk about local losses, sometimes called minor losses. Now remember that in the energy equation, as I've written a few times this semester, we've got the pressure head, the elevation head, the velocity head at 1, plus the head that's added by a pump is equal to the pressure head, elevation head, velocity head at 2. And I sometimes just write H sub F. But when I've done that, I hope, taken pains to remind you that in those cases where I just go straight to H sub F, we were neglecting local losses because they're relatively minor. But the full equation is H sub F plus H naught. H naught is the local losses. And they come into play when the water is changing direction because of a bend in the pipe, when there is a change in pipe diameter. And the way that we estimate the magnitude of the local loss is by multiplying a K value, some coefficient that varies depending on the type of fitting. We can look it up in a table. And you multiply it by the velocity head. Now in a bend like this, the diameter is the same at the inflow and the outflow. So you just use the velocity. The velocity isn't changing in this kind of a transition. There are other cases where the velocity is changing. So if you have a small pipe going into a large pipe, it depends on the table that you're looking at. A lot of the K values would either be calibrated to the discharge flow rate, discharge or inlet velocity, or in some cases the average velocity between the two. So for example, there could be a K value that you're intended to multiply by the difference in velocity between the transition. It depends on the table, and so you'll have those contextual clues, and we'll work an example here to give you an illustration of what that's like. But the energy loss is because it's adding turbulence to the flow when water is changing direction. And in the same way that pipe friction can resist the movement of water by applying a shear stress that opposes the flow direction, so too can we have a reduction in energy because of vortices and turbulence. And if you think about the flow having to reestablish the direction, if there was the streamlines that are going straight down and then it changes direction because of the impact with the edge of the pipe and a smaller laminar layer where the flow is impacting, and just a variety of factors cause additional turbulence that induces a localized reduction in energy. So it can be when water is going into a pipe, it can be when water is coming out of a pipe and discharging into a tank, bends in a pipe, transitions in diameter, and valves. And so we'll look at some of these specific cases. For example, in the case of a contraction where a pipe diameter is decreasing, not only does it depend on whether it's going from a really large pipe to a small pipe, it partly depends on how big is the transition in diameter. For example, if you were going from a 1 meter diameter pipe to a 0.2 meter pipe, that's a pretty big change in diameter. And so you'd see a higher K value for a large change in diameter than you would for a relatively small change in diameter. So like if you're going from a 1 meter pipe to 0.9 meter, the change in diameter isn't so big, and so there isn't going to be as much of a induction of turbulence if it's a relatively gradual transition in diameter. But it also has an effect of whether the transition is tapered. And so here this angle is suggesting that if you had a 60-degree transition angle, there'd be less energy loss than if you just had an abrupt change in diameter without any taper whatsoever. So if you just had it going from a 1 meter diameter pipe to a 0.9 meter diameter pipe, even though that's a relatively small change in diameter, just the fact that it's abrupt would mean that you'd have more energy loss than if it had been a gradual transition. And I think that makes intuitive sense to everybody. Similar situation when you've got a pipe expansion. And we'll look at some of the different fittings that are described here, but the type of valve that you have can vary a lot. You'll notice that in the case of a gate valve that's open, you may only have a K value of 0.2. Compared to a globe valve, you could have a K value of 10. So what that means is that if the water is flowing at 1 meter per second, so water is going at 1 meter per second squared divided by 2G, let me just get my calculator here. It's 1 divided by, so 0.051 meters of head loss if you have a K value of 1. But if you had a K value of 0.2, so if you're running water through a gate valve that's wide open, you'd multiply this by 0.2, and you'd only have 0.01 meters of head loss. So there's not much head loss going through a gate valve that's wide open. But a globe valve that's wide open, if you multiply this by 10, you now have a relatively significant amount of energy loss. So the globe valve that's wide open, 0.51 meters of head loss. So now that's significant and worth keeping track of. Another interesting thing is that if you have a pipe that's changing direction, how gradual that pipe change is, the change in direction, can also have an effect in the K value. And so a really abrupt change in direction where the radius to diameter ratio is 1, what that would mean is if it is changing direction and we're looking at, for example, a 1 centimeter pipe, then we wanted to know what is the radius of curvature for that. If it was also 1 centimeter, then that's where we would have the radius to diameter. The curvature radius to the diameter of the pipe is 1, then you'd have a K value of 0.35. But if you make that bend more gradual, then it reduces the K value because it's just more of a gentle transition, less turbulence, and so the longer that you spread out that change in direction over, it reduces the energy loss to a point, but then it starts going up again, and it's because now you're adding length to the transition. And so they're kind of combining together the added length of the transition with the turbulence that is caused by the change in diameter. So, according to this, the ratio that would reduce the amount of energy loss would be 4 to 1 radius to diameter for a pipe transition where you're changing the direction. Here's a look at the different valve types, and it can help you to understand, for example, why a gate valve may have such a low K value, because it's effectively just a pipe that sometimes you put a gate in front of the flow, and so when it's open, the water is flowing through a straight pipe without changing direction. It's not necked down and narrowing the flow, and so there really is just maybe a little bit of turbulence as the water interacts with this edge or the seat where the gate would be closed up against. But in the case of a globe valve, the water is not only the pipe diameter is larger than the inside of the globe valve, and so it's having to go through this narrower channel, so it's choking the flow because of that, but it's also changing directions a couple of times as it goes through the globe valve. It's going down, and now it has to go to the side, and then changing directions down again. So even when it's open, you still lose a lot of energy through a globe valve. Check valves are used in sanitary sewers and in storm sewers as a way to prevent flow from getting into people's basements. And so they have relatively low flow rate, low K values for swing check valves, but there are these ball type check valves where there's essentially like a little floating, you can think of it as a ping pong ball, although sometimes they're more rugged than a ping pong ball, that it would, when the flow is going the opposite direction, it would seal down an opening, and because there's a really small diameter opening inside of the valve that the water's going through, it has an enormous K value of 70 even when it's all the way open. So there's a lot of different valve types that you just are given the K value for that particular valve, usually by the equipment manufacturer, and the way that you apply it in these calculations is you multiply it by the velocity head at that location. If you have water coming out of a tank or a reservoir and it's just a straight edge discharge, but the pipe doesn't protrude into the reservoir, then the K value that you'll use there is 0.5. But if the pipe does protrude into the tank, you'd use a K value of 1, meaning that there's more energy that's lost if the water has to accelerate through that opening, and it's kind of interesting to think that just moving the pipe into the tank a little bit could cause a reduction in performance, but it can. If you have a tapered and rounded entrance to the pipe, then you can bring the K value down quite a lot, down to 0.04. And then there are some empirical formulas that have been estimated to determine the effect of pipe angle as well. So if you had an angled pipe like this, then it's adding to the energy loss, because just from a straight pipe, you'll notice that it was 0.5 and the same 0.5, but then plus some additional energy loss depending on the angle. Here's just another view of the globe valve to help you understand why the K value is relatively high, because the diameter of the pipe coming in would be larger than the flow diameter within the valve, and then it's having to go through a relatively small opening between the valve plug and the valve seat before it exits out through the discharge end again. And like I said, there are just basically equipment manufacturers who can provide data for the equipment that they sell. They've measured all of these things in the labs or had it tested, and so you can look up the K value for different sizes, may have a different K value. It's not just by category, but it also depends on the size of the pipe and the size of the fitting, and so those details are reported by the manufacturer, and then you multiply it by the velocity head. So let's get some practice with this and also apply Hayes and Williams at the same time. So in this example, we're going to account for both the friction loss and also the local loss. And what we know is that here at location A, we've got a certain amount of pressure, and we know the elevation differential between A and B. It says in the problem statement that B is 12.5 meters higher. So it's downstream, so we're losing energy between A and B due to pipe friction. We're losing energy between A and B because of local losses. We've got a bend, a globe valve, and another bend. So the K values have all been given here. And you can add together the K values. See how this formula is saying the sum of the K values? As long as the velocity at each of the locations is the same, you can add the K values together and multiply it by velocity head. But if you have a variety of different pipe sizes, then you'd need to use the velocity at that particular location. But in our case, all three of these K values are applying to the same 350 millimeter diameter pipe. So the water is going 4 meters per second. We're trying to find out what is the pressure downstream at B. So the pressure at B is going to be less than 650. It's going to be less because of the pipe friction and because of the local losses and because of the elevation difference. All three of those things are acting together in the same way. They're reducing the pressure between A and B. So I'll pause for a moment, and what you're going to do is calculate how much head loss due to pipe friction is there. Calculate how much head loss due to local losses are there, and then put it into the energy equation to find the pressure at location 2. Okay, so oftentimes we'll have problems where the units that are described in the problem statement aren't the same as the units that you need to put into the formula. I've been grading your homework assignments, and some people are doing pretty good about keeping the units straight, and some people I think would do better if they wrote the units when they were also writing the numbers, because then that would help you to see, for example, in the Jane equation. Some people would have K sub S in millimeters, but then D in meters. And then you get the wrong F value if you've got your relative roughness in mixed units. But if you write the units on the paper while you're also writing the numbers, you're less likely to make a mistake. So for example, at the top here, where I'm saying D equals 0.350, well, we were given the diameter in millimeters. But just by emphasizing what the units are when you're defining each of the variables, I think you're less likely to make a mistake when it comes to the substitution stage. Okay, so you can see we've got all of the given details here, and then using the Hazen-Williams method of friction loss estimation, we determined that there's about 43.1 meters of head due to pipe friction, head loss due to pipe friction. And then the local losses are smaller, though not negligible. Between the three fittings that we've got, it's 8.481 meters. And that's largely driven by the fact that we've got this globe valve with a K of 10, which is really high, but like if you were trying to estimate how many fittings the water flows through between some elevated tank on a hillside and your house, there'd be usually dozens of fittings along the way before it gets to the faucet in your bathroom. Lots and lots of fittings and pipe bends and transitions along the way. So local losses can be significant. The other thing that makes the local losses significant here is the water's moving really fast. 4 meters per second is a pretty healthy clip. So we've got a lot of energy loss. Now, if we substitute those two things into the energy equation, so here is the energy equation. I didn't write the H sub P term, the pump term, because we don't have a pump in this problem. But rearranging it to solve for the pressure at 2, now, since the diameter at 1 and 2 is the same, the velocities are the same, so I'm not going to include the velocity head terms when I'm calculating the pressure, but you can see the different components of it. Initially, at location 1, there's 66 meters of head because of that pressure. So from the 66 meters, we're losing 12.5 to the elevation change, 43 meters due to pipe friction, about 8.5 meters of head is being lost due to the local losses, which means there's only 2.2 meters of head remaining by the time we get to that downstream location. And multiplied by the unit weight of water, we've got 21.3 kilopascals will be the pressure downstream. And that's actually a real problem. When we get later on to a little bit more of the real world guidelines, it's usually considered best to keep the pressure above 240 kilopascals just for operational purposes, and should be no lower than 140 kilopascals to avoid contamination of the water network. So at only 21 kilopascals, this is a problem because it's possible that backflow or contamination could occur. So if this is potable water that we're hoping to keep pure and without contamination, then we're kind of in the danger zone at this point at 21 kilopascals. But, you know, at the very least, this is good practice for us to just get some more reps in with using the Hazen-Williams friction loss method and also taking into account the local losses. So any questions there? All right, Moody diagram. I've got a handout for you. There's two questions at the bottom of this, and I would like you to calculate for both of the problems that are described what is the relative roughness and what is the Reynolds number, so we can get some practice using the Moody diagram and trying to be really accurate. We've only got 6 minutes, but that should be plenty of time. So to calculate Reynolds number, you'll need to know the fluid velocity, the diameter, and the kinematic viscosity. And in the first problem, it's water. In the second problem, it's kerosene. So you've got the kinematic viscosity for both of those. On the first one, you can see on the whiteboard I've written that the relative roughness is 0.001. So that's just the K sub S divided by the D. So over here, on the vertical axis on the right side, we're going to start with the 0.001 curve and follow it until we intercept whatever Reynolds number is applicable here. And for the velocity that's described, oh, actually, we've got a flow rate. So the flow rate, 0.2827 liters per second. So convert that to cubic meters per second, divide by the pipe area. We've got the velocity, 0.177 meters per second. And that was selected so that we'd have this exactly 8,000 Reynolds number. That's why I chose such a strange flow rate, because I wanted it to be something that we could go exactly to 8 times 10 to the third, 8,000. So you can see that if we follow this red line, which is the 0.01 curve, and we're looking for where does it intersect 8 times 10 to the fourth, and then trying to be as precise as possible, which is easy because that happens to be coincident with the 0.034 line. So that's the one with water. Now with kerosene, I'll just jump straight to the chase. If you've got the kerosene, the relative roughness is 0.0004 is the K sub S to D. And then the Reynolds number for the kerosene is 1.5 times 10 to the 7th. Okay, so on this one, we're again working with the Moody diagram, but we're on the 0.004 curve. And this is in the the rough turbulent zone. So we're intersecting the 1.5 times 10 to the 7th. So it is, here's the 10 to the 7th, 1.5, and then it's just going over to 0.016 for this kerosene going through galvanized pipe. All right, well, that was just a little extra practice. It's 1:50. We're out of time. Your homework is due on Wednesday. If you've got questions, please stop by. Give me a call on Teams. Send me an email. I enjoy spreadsheets, and so let me help you if I can help you. All right. Have a good day.